Hello, this is Jennifer Martinez, and today's video we're going to go over the Schmidt process. The Schmidt process is an algorithm that gives you an orthogonal basis or an orthonormal basis for a subspace W. It's going to go backwards from the last section. We're going to actually find the orthogonal basis. If you look at this example, for instance, let W be the span of x1 and x2, and x1 and x2 are independent, but they are not orthogonal to each other. So you're going to get an orthogonal basis for W. So what you're going to do is, given a basis of x1 through xp, of a non-zero subspace, again, they don't need to be orthogonal, of Rn, we're going to define V1 as x1, and then V2, we're going to take x2, and we're going to subtract the projection to ensure it to be orthogonal. The projection along V1, that is. And then we're going to do the same thing for V3. V3, the next one, we're going to take our next vector and we're going to subtract the projection along V1 and subtract also the projection of x3 along V2. That's what this is. When we do this, V1 through VP becomes an orthogonal basis for W. In addition, the span of x1 through xk for 1 to k is going to equal to the span of v1 through vk. We'll see this in a minute. So let's go ahead and construct an example in R2 so we can see or visualize what's going on here. So we're going to again let W equal the span of x1 and x2, where x1 is 4, 0 and x2 is 2, 3. This time we're going to construct an orthogonal basis v1, comma v2 for W, where W is the span. The span of x1, x2 is all of R2. We can see that they're independent. So it is a basis for R2. Okay, so let's start. So let's let V1 equal x1. V2 is x2 minus the projection along the line V1. Okay, so let's look at x2 dotted with V1, which is the same really as x2 dotted with x1. So that would be 4 times 2, which is 8, plus 0, so it's just 8. And then V1 dotted with itself is going to be V1, which is the same thing as x1 dotted with itself, which is 16 plus 0, 4 times 4, plus 0 times 0. So we get 1/2. So x2, I should say V2, is x2, which is, let's just write that first, x2 minus 8 over 16, which is 1/2 of V1. Since x2 is in W, and we're subtracting off the projection of x1, or the projection of V1, then V2 is going to be orthogonal to that x1 or that V1. Kind of interesting. So here, by the way, V2, if we now put in what x2 is 2, 3, and V1 was 4, 0. And computing this, we get 2, 3 minus half of 4 is 2, 0. So this looks like it's going to be 0, 3. I picked a simple case so we could just visualize that. We can draw it. So let's go ahead and see what we got. x1 was 4, 0. So there it is there. x2, x1. x2 is 2, 3. So we're going to let, again, v1 be x1. So this is actually v1. Let's do it in green. And then we're going to say v2 is 0, 3. There it is, right there, 0, 3. That is v2. You can see v1 and v2 are orthogonal to each other. Did a simple example. And if we project x2 down onto v2, which is what we were doing here, take x2, this quantity right here, we took x2 dotted with v1 over v1 dotted with itself. So that's the projection of x2 onto v1, which I'll do in a different color, maybe blue, right there. That would be x2 hat, we can call it. We can see that that dotted line, that is that v2, right? If we take that x2 and subtract the projection, so here's x2, we're going to subtract, this is, take the negative, start here and take the negative of x2, and you do get v2. So there it is. The two quantities in green is what we end up with, and they are orthogonal to each other. And they do form a basis for our same subspace. They form a basis for R2. And the last part of our theorem says, in addition, the span of V1 through any Vk is equal to the span of x1 through any xk, all the way from k from 1 to p. So it's equal to each other along the way. So in other words, the span of v1 is equal to the span of x1. Well, that's true because they're the same. And then the span of v1 comma v2 is equal to the span of x1 comma x2, and these are vectors. And you can see that both of these are the span of R2, so they are the same. So let's look at an example in the book where x1 and x2 are in R3. So let's let the same thing, W, be the span of x1 and x2, where x1 is 360 and x2 is 122. You can see that they are not orthogonal to each other. The dot product is not 0. We're going to construct an orthogonal basis, one that is orthogonal, and we're going to call it V1 and V2 for W. And the construction of W is on the right here in figure 1. This is a construction of the orthogonal basis for W, but right now we're just going to look for the green in W. This one is 360. 3, x1 is 3, x2 is 6, and y is 0. And then this x2 point is 1, 2, and then over 2. So we're going to set it up again that v1 is x1, and we know x1 is 360. And they have that there in blue. So I'll just add an arrow there. And V2 is x2 minus, this is the projection of x2 onto the vector v1. We can call it the projection of x2 onto w1, where w1 is just the span of your x1. x2 dotted with v1 is just x2 dotted with x1, since they are the same. So I'm going to just use these two vectors and dot them together. So that would be 3. highlighted in blue. So that would be 3 times 1, which is 3, plus 6 times 2, which is 12, plus 0, so that's 15. And V1 dotted with V1, there's V1, is going to be 3 squared, which is 9, plus 6 squared, which is 36, which is 45. So we have V2 is going to be the x2 minus the 15 over 45 V1, which is, reducing that, get 1/3 V1. Computing that vector, we get V2 is equal to x2, which is the 1, 2, 2, minus 1/3 of V1, which is 3, 6, 0. Computing that, we get 1/3 of V1 is 1, 2, 0, and then subtracting these two vectors, we get 0, 0, 2. So we just constructed an orthogonal basis. If we take V1 dotted with V2, we do get 0, 3, 6, 0, dotted with 0, 0, 2, which is 3 times 0 plus 6 times 0 plus 0 times 2, which is indeed 0. So we know that V1 and V2 are orthogonal with each other. If we actually graph V2, which is 0, 0, 2, so V2 is sitting here, and we look at the projection of x2 along W1, where W1 was the span of x1, I forgot to add here, times V1. We look at this projection, so here in green is x2, and we want to project that onto V1, which is the 0, 3, 6. You get this dotted line in orange, which is the same as what V2 is, right? Or you can subtract that again, and you get this distance, putting that at the 0, 0, 0 mark. So in orange there is V2. Notice how V1 and V2 are in the W plane, and V1 and V2 do span all of W. So it is true, the second part of it, that the span of x1, x2, which is W, is equal to the span of V1 and V2. By the way, we also know that this is the span of just V1. Right? The span of x1 is the span of V1, since they are the same. So we found the orthogonal basis. The orthogonal basis is V1, which is 3, 6, 0, and V2, which is 0, 0, 2. That's the orthogonal basis for W. If you want to find an orthonormal basis, you just have to normalize these two vectors. So if they ask for an orthonormal basis instead of an orthogonal basis, I would just take my V1 and divide it by, so here's my V1, 360, and divide it by the distance of V0, which would be 1 over the square root of V1 dotted with V1 times V1, which would give us 1 over square root of 45 times V1. Writing what V1 is and reducing this, here would be U1. Doing the same thing for U2, you can see that you get 0, 0, 1. These two are orthogonal.
Their distances are 1, so U1 and U2 are called an orthonormal basis for W.